All charges produce an electric field. These are vector fields given by the letter E. The field can exert an electrostatic force on another charged particle, and that force is shown by this equation, E equals force over charge. And the units are in newtons per coulomb. Electric fields can be represented by electric field lines. There are rules, however, in drawing these electric field lines. First, the electric field lines go from the positive charge to the negative charge. Second, the electric field vector is always tangent to the electric field line and in the same direction. And lastly, in a plane perpendicular to the electric field, the density of the lines represents the magnitude of the field. In other words, field strength. Here are some examples of electric fields. These are opposite charges, and you see the electric field going from positive to negative. These are the same charges, and you can see that the electric fields come off each positive charge, but then repel each other as they get closer. Here's an electric charge with a charged plate, and again, the field goes from the positive charge to the negative plate. And here's a positive and negative plate with the electric field going from positive to negative. Now, what about an electric field due to a point charge? That could be positive or negative. Well, we know from Coulomb's law that the force of that field is equal to 1 over 4 pi epsilon sub 0 times Q1, Q2 over R squared. So if we consider this to be Q1, and the field is radiating out from that, and we have a second charge here, Q2, what is the field at Q2? Well, we also know that E is equal to force over Q. So if we combine and rearrange this, we find the electric field of a point charge is equal to 1 over 4 pi epsilon sub 0 times Q over R squared. Now, electric fields also undergo the principle of superposition. So if you have multiple charges present, number of charges, the net electric field is the vector sum of each individual electric field. So E net would be equal to E of charge 1 plus E of charge 2 plus all the way out to E of charge n. And again, it's the vector sum. Now let's discuss electric fields due to a dipole. When you have two opposite charges separated by a distance, you have a dipole. So if you have a negative charge and a positive charge, and these are separated by a distance d, you have a dipole. And let's look at the electric field. So the electric field again goes from positive to negative. So we'll just put this in. And these go out that way, and these are come in this way. Okay, so let's say we have a point P way out here, and P is a distance. We'll call that R from the center of the dipole. Okay. Now, P is going to feel the electric field and the force from both charges. So we have the field from the positive charge, and we also have the electric field in the opposite direction. That's E from the negative charge. And so we have two separate electric fields. So using the principle of superposition, the net electric field on P, on point P, is equal to the sum. And if you work that out, you get 1 over 2 pi epsilon 0 times QD over R cubed. And again, D is the length of the dipole from positive to negative charges, and R is the distance from point P to the center of the dipole. Well, QD we define as the electric dipole moment. And that is written as small p, and that's a vector. So D has to also be a vector. And the units for those are obviously Coulomb meters. So then we can write the electric field for a dipole as 1 over 2 pi epsilon 0 times P over R cubed. Now we're going to look at an electric field due to a line of charges. So instead of a point charge, we will look at multiple charges on a one-dimensional object, such as a rod or a ring of charges. But first, let me note that for larger objects with multiple charges, it is easier to look at the charge density instead of the total charge on the object. So for a one-dimensional linear object, we use the linear charge density, and that is given by lambda, which is equal to Q over S, which has the units of Coulomb meter. So if we have a rod, then S is the distance along that rod, or if we have a ring, S is a segment on that ring. For a two-dimensional object, we're looking at a surface charge, and so we use what's called a surface charge density, and that's given by sigma, which is equal to charge per area. So the units there are coulombs per meter squared. And for a three-dimensional object, looking at a volume, we use a volume charge density, and that's given by rho, which is equal to charge per volume. So that's coulombs per meter cubed. Okay, so let's get back to our line of charges. And in this case, we're going to look at a charged ring. So let me go over this diagram briefly. We have a ring of charges down here, and we're looking at a segment ds, and that ds has a charge of dq. The ring has a radius of capital R. We're looking at a point at a distance from the ring, and that is a distance of R from the segment on the ring, and it makes an angle of theta with the axis of the ring. And that segment produces a segment of the electrical field dE shown in that direction. And in the calculations, we use the linear charge density, which again is equal to Q over S, or in this case, dQ over ds. So the textbooks go through the actual calculations, including the integration, to derive the formula for the electric field. I'll just tell you what they do. To determine the electric field at point P, we must split the ring into tiny segments, ds, with tiny charges, dq. Then we need to find the components of the electric field, dE, that pass through P. All of these will produce dEs passing through P. We can then cancel out all the horizontal components due to opposite signs. So in this ring, you have a positive E and a negative E, a positive E and a negative E. All the horizontal components actually cancel out to give you a net electric field of 0. The only electric field components left are vertical components, and this is the z-axis. It's a z right there. So we then have to integrate the vertical components along z to get the net electric field at P. So when we do that, we find that the electric field E is equal to Q times Z over 4 pi epsilon 0 times Z squared plus R squared to the 3/2. So this is the electrical field for a charged ring. Now, if the ring has a positive charge, then the electric field will point away from the ring. And if the ring has a negative charge, then the electric field will point towards the ring. That's because E goes from positive to negative. Now, if we look at this equation, if Z is much, much greater than R, if our point P is very far away from the ring compared to the radius of the ring, then 1 over R squared becomes very, very small to the point where we can ignore it, and E then becomes 1 over 4 pi epsilon 0 times Q over Z squared. Again, that's when point P is very, very far away from the ring compared to its radius. And if you recognize this, this is just basically the electric field of a point charge. So in other words, when you're very far away from a charged ring, it almost seems like that ring is just a single point charge. The other thing is that if Z equals 0, in other words, you're right in the center of the ring, there is no vertical field along the z-axis. The only field components are along the x-axis, and they all cancel each other out. In that case, electric field is equal to 0. Now let's go to 2 dimensions and look at an electric field due to a charged disk. So we would use the surface charge density in this case, which is equal to charge per unit area. And so we have a charged disk of radius r, and we look at a small ring inside the disk, a segment dr that is at a radius r from the center, and we have a point P that we're considering, and the charge on the disk gives us an electric field segment dE up here. So if we go through the same calculations that we did for a ring of charges, then we would find that the electric field for a charged disk is equal to sigma over 2 epsilon 0 times 1 minus z over the square root of z squared plus r squared. And this is the electric field for a charged disk. Now, let's say the disk is very large. R goes to infinity. It becomes very huge. Then what happens is that this part of the equation with R going to infinity becomes 0, and our electric field simply becomes sigma over 2E0. Also, let's say Z is equal to 0. So we're down right in the center of that disk. Well, once again, if Z is equal to 0, the electric field becomes sigma over 2 epsilon 0. So these two equations are the same, and basically that's equivalent to the electric field of an infinitely large sheet with uniform charge on it on one side, actually. So that would be as if you had a gigantic sheet with a charge on one side. That's what these equations become equivalent to. Now, let's say you have an electric field and you decide to put a point charge in that field. Well, what happens is that field will exert a force on the charge given by force equals Q times E, as was stated before. And if Q is positive, then F, the force, is in the same direction as E, the field. And if Q is negative, then F is in the opposite direction as E. Okay, now let's put a dipole in an electric field. So if you look at this diagram, you can see the negative and the positive charges in the electric field. It's at an angle theta. The dipole moment is shown there. The charges are a distance d apart, and the center of mass of the dipole is shown. So the electric field is exerting a force on both negative and positive charges. In this case, the force is a positive QE, and down here, the force is a negative Q times E, because the force is going opposite to the electric field. However, the center of mass of the dipole doesn't move because both these forces are equal. So we end up with a torque, tau, due to the forces on the positive and negative charges. And this torque is equal to the dipole moment times the electric field. In this case, it's the vector cross product. And before we go on with this, I just want to review the multiplication of vectors, the dot product and the cross product. So the multiplication of vectors, the first one is the dot product. And that's where we have vector A dot vector B. And the magnitude of that would become AB times cosine theta, where you have vector A, vector B, and this is theta. Basically, what you're doing is you're multiplying A times the component of A that is in the direction of B. So you would drop this down to B, and that would be B cosine theta. So that's where we get this. This is the component of A that falls along and is in the same direction as vector B. So if you notice that if theta is equal to 0 degrees, then A dot B is equal to just AB, because cosine of 0 degrees is 1. And if theta is equal to 90 degrees, then A dot B is equal to 0, because the cosine of 90 degrees is 0. And the other thing to note is that a dot product gives you a scalar answer, a scalar number. The result is not a vector. So let's look at the cross product of a vector. And we're talking about A cross B. And that is actually equal to AB times the sine of theta. And this does give a vector. And this vector is perpendicular to the plane of A and B. So if you remember, we can use the right-hand rule to find the direction of this vector. So if we have A and B, and we cross these two, we take our right hand, rotate A into B, and our thumb would point into the page. So that would be given by that. So the resulting vector C would be into the page. And again, if theta is equal to 0, A cross B equals 0. And if theta is equal to 90 degrees, A cross B is simply equal to the magnitude of AB. So we're going to be using both of these vector products in our discussion of torque. So let's get back to our discussion of the torque on a dipole in an electric field. So this would equal to P E times sine theta. Now let's look at the potential energy of a dipole in an electric field. It turns out that the potential energy is equal to minus the dipole moment times E. And again, that becomes a scalar quantity, which is equal to minus P E times cosine theta. And it turns out that we define U equals 0 when theta is equal to 90 degrees, when a dipole is perpendicular to the electric field. So you have P and you have E. Then U is minimum when theta equals 0 degrees, because then we get U is equal to a minus P E, and U is maximum when theta is equal to 180 degrees, because then we get U is equal to a positive PE. And again, U is 0 at 90 degrees. Now let's talk about the work done with a dipole. So when a dipole rotates, work is being done. And if it's done by the electric field on the dipole, then work is equal to minus the change in potential energy, which becomes minus U final minus U initial. However, you can also have work on a dipole by an outside agent. In other words, someone or something is turning the dipole within the electric field. So if it's being done by an outside agent, then the work is opposite from what you would get when it's done by the electric field. In other words, the work on the from the outside agent is equal to minus W, which is then equal to U final minus U initial. Let's do some problems. Two charges, Q1 equals 5 times 10 to the minus 6 coulombs, and Q2 equals minus 4 times 6 to the minus 6 coulombs, are separated by 3 meters on the x-axis. What is the electric field at a point 3 meters above Q2 on the y-axis? What is this direction? So you can see I've drawn a diagram here. You have Q1 and Q2 separated by 3 meters, and we want to find the electric field at a point P 3 meters above Q2. So we know the electric field at P is equal to the electric field due to Q1 plus the electric field due to Q2. So let's start with finding the electric field due to Q1. So the electric field is equal to 1 over 4 pi epsilon sub 0 times Q1 over r squared. And that's equal to 8.99 times 10 to the 9th. And the charge is 5 times 10 to the minus 6 coulombs over, okay, now r squared, the distance would be the hypotenuse, and we know that that distance is equal to the square root of x squared plus y squared. So that would be 3 squared plus 3 squared, which is equal to the square root of 18. And since we're using r squared, or in this case d squared, then d squared, which is r squared, is equal to 18. So we'll put that in here. So we get E1 comes out to be 2.5 times 10 to the third newtons per coulomb. Now, you can see up here that the electric field has a direction in the x and y axes. So we need to break that down to add the vectors. So E1 is equal to E1x times unit director I plus E1y times unit vector j. So that's equal to E1 2.5 times 10 to the third times cosine 45 degrees. That's how we find the x direction times unit vector I plus E1, which is 2.5 times 10 to the third times sine 45 degrees to find the y direction times unit vector j. And this comes out to be 1.78 times 10 to the third I plus 1.78 times 10 to the third j. So this is our vector due to Q1. Now let's find E2, the electric field due to charge 2. Well, we know that the electric field due to charge 2 points down in the minus y direction because Q is a negative charge and the electric field points towards it. So in this case, E2 is equal to E2 in the x direction plus E2 in the y direction. In this case, E2 in the x direction is 0 plus E2 in the y direction equal to 1 over 4 pi epsilon 0 times Q2 over r squared. So that's equal to 8.99 times 10 to the ninth times Q2, which is a minus 4 times 10 to the minus 6 coulombs over r squared in this case is 3 meters. That's r, so r squared is 9. So this becomes 0 in the I direction minus 4.0 times 10 to the third j. So to add E1 and E2, so E at P is equal to E1 plus E2. So that would be E1 in the x direction plus E2 in the x direction plus E1 in the y direction plus E2 in the y direction. So that's equal to 1.78 times 10 to the third plus 0 I plus 1.78 times 10 to the third minus 4.0 times 10 to the third j. That comes out to be 1.78 times 10 to the third I minus 2.22 times 10 to the third j. So this gives us E in its x and y components. We want to know the total magnitude of E. So that would be equal to the square root of 1.78 times 10 to the third squared plus minus 2.22 times 10 to the third squared. And if you go through that calculation, you get E at P is equal to 2.8 times 10 to the third Newton coulombs. That's the total magnitude of the electric field at P due to Q1 and Q2. Now we want to know the direction. Well, we know that the tan theta, the tan of the angle between the two components, is equal to y over x, which is equal to minus 2.22 times 10 to the third over 1.78 times 10 to the third, and that becomes minus 1.25. So the arctan of a minus 1.25 turns out to be a minus 51 degrees. So that's the direction of theta. So if we go back to our drawing, okay, now we know the magnitude, we know the direction, so we can say that our final vector is at an angle of minus 51 degrees, which would be about like that, and this would be the final electric field at P. Let's do another problem. A ball of mass 0.5 grams is hanging by a massless thread in a horizontal electric field of magnitude 600 newtons per coulomb. It is angled at 25 degrees towards the electric field and not moving. What is the charge on the ball? So by saying it's not moving, it means that the ball is in equilibrium. And that means that the sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. But first, let's draw a free body diagram to show the forces. So here's your ball, and you have your tension pulling on the string. You have the weight, mg, pulling down, and you have the electrostatic force due to the charge on the ball in the electric field. So if we look at our forces in the x direction, we have the electrostatic force has to equal the tension in the x direction, okay? Because this is tension in x, this is tension in the y direction. So that's equal to T times the sine of 25 degrees. So we get force, electrostatic force is equal to 0.42 times T. Now let's look in the y direction. In this case, we have the weight of the ball has to equal the tension in the y direction, which is equal to T times cosine 25 degrees. Well, we know the weight of the ball, which is 0.5 times 10 to the minus 3 kilograms times g, the graph is equal to t times 0.91. So we can actually solve for t now, and we get t is equal to 5.4 times 10 to the minus 3 newtons. If we then take this value for t and substitute it into the equation for the electrostatic force, we get electrostatic force is equal to T, which is 5.4 times 10 to the minus 3 times 0.42, or our electrostatic force is equal to 2.3 times 10 to the minus 3 newtons. Now, we also know that electrostatic force is equal to Q times E. And we're looking for Q. So we can solve that Q is equal to force over E. And we know those two terms. So Q is equal to force, which is 2.3 times 10 to the minus 3 over our electric field, which was given as 600. And if we go through that, we get the charge is equal to 1357 times 10 to the minus 3 coulombs, or we'll just say it's equal to 1.4 times 10 to the minus 6 coulombs, or 1.4 microcoulombs. Now this is the magnitude of the charge, but we actually know that the charge itself has to be negative. And the reason for that is if we go back to our diagram, obviously the electrostatic force is pointing opposite of the electric field, therefore it must be a negative charge. If it was positive, the force would point with the electric field and the ball would be displaced in the other direction. Our next problem. Two parallel and oppositely charged plates have an electric field between them of 10 kilonewtons per coulomb. The plates are 1 centimeter apart. An electron is shot along the negative plate at 10 to the 6th meters per second. Where will it hit the positive plate? So basically what we're dealing with is projectile motion. And if you remember, we separate the two movements in the X and Y directions. We treat them separately. And the other thing we know about projectile motion is that time relates the directions of motion. So what are we given in this problem? Well, we know the electron charge is equal to the elementary charge of minus 1.6 times 10 to the minus 19th coulombs. We can find that the mass of an electron is equal to 9.1 times 10 to the minus 31 kilograms. We're given that the electric field is equal to 10 kilonewtons per coulomb, which is 10 to the 4th newtons per coulomb. We're given our initial velocity in the x direction is 10 to the 6 meters per second. Our initial velocity in the y direction is 0. And the distance that it travels is the separation of the plate, which is y, is equal to 1 centimeter, which is 10 to the minus 2 meters. So this is what we know. So first thing we can determine is acceleration. Acceleration is equal to force over mass. And in this case, force is equal to Q times the electric field over mass, which is equal to Q of the electron is minus 1.6 times 10 to the minus 19th times the electric field, which is 10 to the 4th over the mass, which is 9.1 times 10 to the minus 31. And so we end up getting is that the acceleration of the electron is equal to 0.176 times 10 to the 16th meters per second squared, or 1.76 times 10 to the 15th meters per second squared. Now that we know the acceleration, we can find the time it takes for the electron to go from the negative to the positive plate, because time is the common factor. So we can use the equation y equals v0 in the y direction times t plus 1/2 at squared. So we know that y is equal to 10 to the minus 2 meters is equal to, well, v0 times t, v0 is 0, plus 1/2 a, which is 1.76 times 10 to the 15 times t squared. And again, we're looking for t. And if you go through that calculation, you find that t is equal to 3.4 times 10 to the minus 9th seconds. Now that we know the time of travel, we can use that to find how far the electron travels in the x direction. In other words, where it will hit the positive plate. So we use the formula x equals velocity in the x direction times t, which is equal to 10 to the 6 meters per second, which we're given, times t, which is 3.4, times 10 to the minus 9th seconds, which we calculated. And we end up getting x is equal to 3.4 times 10 to the minus 3 meters. That's where the electron will hit the positive plate. Let's do another problem. An electric dipole with opposite charges of magnitude 2 times 10 to the minus 6 coulombs are separated by 1 centimeter. It is placed in an external electric field of 2 times 10 to the 5th Newton coulombs. What is the maximum torque on a dipole due to the electric field? How much work is done by an external agent if the dipole is rotated 180 degrees? Assume the dipole starts at 0 degrees. So here you see the diagram of our dipole, a minus and a positive charge in the electric field. So we want to know what the torque is on a dipole, and the torque is equal to P cross E, which is equal to PE times sine theta. Now, it asks what is the maximum torque? Well, we know the maximum is when sine theta is equal to 1 or theta is equal to 90 degrees. So if we put that into the equation, the maximum torque is going to be equal to PE times sine theta. Well, P is the dipole moment, and that's Q times D times the electric field times sine theta. And in this case, sine theta is going to equal 1. So the maximum torque is T is equal to Q, which is the charge, 2 times 10 to the minus 6, times the distance, which is 1 centimeter, or 10 to the minus 2 meters, times E, which are given as 2 times 10 to the 5th newtons per coulomb, times the sine of 90 degrees is 1. So our torque maximum ends up being 4 times 10 to the minus thirds Newton meter. Now it then asks how much work is done by an external agent if the dipole is rotated 180 degrees. So in the electric field, we're taking a dipole that starts at 0 in this direction, and we're flipping it to go in the opposite direction. So we're going from 0 to 180 degrees. Well, work done by an external agent is actually equal to minus the work done by an electric field, which would then be equal to U final minus U initial. We know that U is equal to minus PE times the cosine of theta. So what we have is that the work by the external agent is equal to U final, which is minus PE times the cosine of 180 degrees, minus U initial, which is minus PE times the cosine of 0 degrees. That gives us minus PE times a minus 1 plus PE times 1, which gives us 2PE, which is equal to 2 times the dipole, which is QD, times E. So we get 2 times Q, which is 2 times 10 to the minus 6, times the distance, which is 10 to the minus 2, times E, which is 2 times 10 to the 5th. And this comes out to show that the external work done is equal to 8 times 10 to the minus 3 joules. Let's do one more problem. An electron starts 100 centimeters from a point charge of 1 times 10 to the minus 9th coulombs. What is its speed when it is 20 centimeters from this charge? So the electron starts at 100 centimeters away from charge Q, and we want to know what is its speed when it's 20 centimeters away. Well, when we think about finding speed, v, we have to start thinking about the kinetic energy, which contains v in the formula. And then we can use conservation of energy to try to find v. Because with conservation of energy, we know that the total energy remains constant. So any change in potential energy plus any change in potential energy has to equal 0. So in this case, we're saying that the kinetic energy at 20 centimeters plus the potential energy at 20 centimeters has to equal the kinetic energy at 100 centimeters plus the potential energy at 100 centimeters. Now, in general, potential energy is equal to minus PE, which is equal to minus QD times the electric field. So in this case, we have minus Q times the distance, which we'll call x, times the electric field, which is the charge, which is in this case the electron, over 4 pi epsilon 0 times x squared. So 1x cancels out, and we get the potential energy is equal to minus QE over 4 pi epsilon 0 times some distance x. So if we go back to our equation, here we have that the kinetic energy at 20 centimeters is 1/2 mv squared, has to plus the potential energy, which is a minus QE over 4 pi E0 at x at 20 centimeters, has to equal kinetic energy at 100 centimeters with electrons started at 0, so the velocity is 0, so that's 0, minus QE over 4 pi epsilon 0 times x, which is at 100 centimeters. So we can then bring this value over to this side of the equation, and we get 1/2 mv squared is equal to QE over 4 pi epsilon 0 times 1 over x at 20 minus 1 over x at 100. So now we can put some numbers in such that 1/2 mv squared is equal to 1 over 4 pi epsilon sub 0 is equal to 8.99 times 10 to the 9th times q, which is 1 times 10 to the minus 9th times e, which is 1.6 times 10 to the minus 19th times 1 over, well, x at 20 is 20 centimeters, which is 0.2 meters, minus 1 over x at 100 is simply 1 meter, so that's 1. So this becomes 1/2 mv squared is equal to 8.99 times 10 to the 9th times 1 times 10 to the minus 9th times 1.6 times 10 to the minus 19th times 4, or 1/2 mv squared is equal to 57.5 times 10 to the minus 19th. So solving for v squared, That's equal to 2 times 57.5 times 10 to the minus 19th over m, which is the mass of the electron, which is 9.1 times 10 to the minus 31, or v squared comes out to be 12.2 times 10 to the 12th. And if we take the square root of that, v is equal to 3.6 times 10 to the 6 meters per second.